Okay, we have our last video from the Unit 11 Matrices review, and it's asked us a couple of things. The first part says, given the matrix A equals 7, 8, 4, 6, it wants us first to find the inverse. So in order to find the inverse, we have to start with the determinant. So we have to find the determinant of A, and that's going to be our 7 times 6, which is going to be 42, minus 8 times 4, which is 32. So our determinant is going to be the number 10. Now that we have our determinant, we can find our inverse, and our inverse is going to be 1 over our determinant times our flippy matrix, which is our adjuvant. So we have to take our 7 and 6 and change places. We have to take our 8 and 4 and change signs. Now we can multiply these right now and get fractions, just like we did in the last example, or we can see if it might be easier to leave them out front and use this matrix for the next part without multiplying first. It's really up to you how you want to go about it. So let's see what would happen if we leave it with the fraction out front, that's scalar undistributed, and go ahead and use this. So the second part of this question is asking us to use this inverse to solve the simultaneous equation. 7x plus 8y equals 39, and 4x plus 6y equals 23. So in order to solve these simultaneous equations, we have to write them as matrices. So I'm going to go ahead and take all of the coefficients from these equations, 7, 8, 4, and 6, excuse me, and those are being multiplied by the variables x and y. So my x's were lined up, my y's were lined up, so now when I multiply these matrices together, 7x plus 8y, that's what I've got, and 4x plus 6y, that's what I've got here. So this works perfectly, and these equal the matrices on the matrix on the right. We have 39 and 23. So I can give these matrices names instead of just their matrix here. So I can call this A, I can call this X, and I can call this B. It really doesn't matter what you call it. But I know that if I multiply A by X, it's going to give me the matrix B. So if I want to undo this X, I have to multiply it by A inverse. I have to pre-multiply it. So if I want to do that on the left, I also have to have pre-multiply B by A inverse on the right. So X is going to be A inverse times B. So let's go ahead and write that out using our matrices. So matrix X is going to be A inverse, which I already know is up here, 1/10, 6, -8, -4, and 7, times matrix B, which is 39, 23. Not very pretty, but it's there. All right. Now let's go ahead and multiply this out. So we're going to multiply our matrices together before using our scalar, just in case it's easier. I don't really know. Let's find out. It's up to us which order we want to do this in. So I'm going to multiply these first, and then I'm going to distribute my scalar later. So first I have to do 6 times 39. That's my first number here. 6 times 39 is going to be 234, plus -8 times 23, which is going to be -184. Then we're going to take 39 times -4. This is going to give us -156, I believe. And then we're going to have 7 times 23, which is 161. Let's see how this simplifies here. So we have 1/10 times 234 minus 184. So the 4's cancel out, so we just have to look at 230 minus 180. So 23 minus 18 is going to be 5. So this is going to be 50. And on the bottom here, we're doing 161 minus 156. Let's see what that's going to equal. It's going to equal the number 5, I believe, which is quite convenient because now when we finally decide to distribute our scalar, we just take each of these numbers and divide it by 10. So x, which is the matrix xy, is going to equal 50 over 10, which is 5, and 5 over 10, which is 1/2. And so now comparing elements side by side, I know x is 5, and I know y is 1/2.